section 11.1. So we did 11.2 because I thought last year I did it in the same order as the textbook, and the order didn't make sense to me. I'd rather start locally and move out. Locally are planets, asteroids, meteors. Now we're going to move out the sun and other stars. So the first question is, what is a star? Well, basically a star is a nuclear reaction in space. It's a fusion reaction. There's two main types of nuclear reactions. There's fusion and there's fission. Fission is when you split big atoms into smaller atoms. Fusion is when you combine small atoms into bigger atoms. Stars are fusion reactors. They're nuclear reactors in space. Stars are made up of hot gases that are reacting, and when they react, they give off heat and light. The sun is a star. Special because it's close and it looks so much bigger and brighter. But really, it's just a pretty middle of the road, average star. Not very big, it's a little on the small side. What do you mean by an average star, Mr. Duick? Well, Brady, let's talk about the types of stars. Okay? First of all, stars vary from small to, holy smokes, massive. Small stars live much longer. So the first thing, and you can maybe put a little star next to this, no pun intended, or this is something you want to know, the size of a star dictates its life cycle. Bigger stars actually burn out faster. And Matt, that's kind of counterintuitive. You're writing this down, of course, yes? That's kind of counterintuitive because you might think, wouldn't a bigger star have more gas and burn longer? Actually, because it's bigger, it burns faster. Smaller stars last longer. Stars vary in color. Red is, well, what's cooler? A red flame or a blue flame? So just like flame, red is cooler, blue is hotter. Now, at nighttime, when you look at stars, you don't notice colors. You need some pretty good instruments, Sierra, to detect this, but we can. So stars vary in size. That was the first thing. Stars vary in color. Stars also vary in luminosity. Know what the word luminosity might mean? Yeah, how bright they are. So we can categorize stars by size. We can categorize stars by temperature. We can categorize stars by brightness, by luminosity. Here's a fairly intermediate star. This is a picture I stole from your textbook. How does a star start out? Well, the first thing that happens is you have a nebula collapsing. A nebula collapses. That's situation number one. What's a nebula? A massive, how massive? Like bigger than our solar system massive. A massive cloud of gas and dust and debris. And because all mass has gravity, slowly all these masses act their gravity on each other, and slowly they condense and they compress and they condense. That nebula compresses. You eventually, with all that mass, with all that gas, get pressure on the inside. And if that pressure gets high enough, fusion occurs. You get a self-sustaining nuclear reaction. So here's the picture. Here's the nebula. By the way, the length of the number of dots is to show you sort of how much time it takes. So nebula lasts for quite a while. Slowly the nebula collapses, and then all of a sudden fusion occurs. And then we have what we call the main sequence stage. This is by far the longest part of a star. So this isn't showing you that the star is moving around. What we wanted to try and do on one picture is to give you an idea, Mason, of how long each life cycle section is. each life cycle section. The longest one, by far, is the main sequence stage. What's the main sequence stage? Star is doing its thing. The sun is in its main sequence stage. It's giving off light, it's giving off heat, it's burning its own fuel, but it's a happy camper. Then, towards the end of a star's life cycle, it starts to run out of, what's capital H2? What element is that? Hydrogen. Stars are almost all hydrogen. The rest of them is almost all helium. There's other stuff, though, too. And when it starts to run out of hydrogen, you see there's a constant tug of war. Inside the star is a nuclear reaction pushing out. But there's so much mass that gravity is pulling it in, and so you have this tug of war between the reaction and between gravity. But as you're burning up hydrogen, as you're burning up mass, the gravity is getting lesser and lesser and lesser and lesser and lesser, and eventually there comes a specific point when the nuclear reaction pressure outwards from the center is bigger than the gravitational pressure inwards from the outside. And we have an expansion to a What color do you think a red giant is? Is it hot or cold compared to most stars if it's red? Do you think it's big or small compared to most stars? How do you know? Because in physics, we know how to name stuff. Red giant. Oh, biology drives me crazy. Endoplasmic reticulum. What the heck is that? Why couldn't you have given it a name that makes sense? You'll hear me go on a rant. Okay, but not now. So what happens is the nuclear reactor pressure has now been bigger than the inward collapse of gravity. The star starts to expand, but as it starts to expand, that nuclear reaction was caused by the pressure of gravity. Since it's expanding, since there's less pressure, that nuclear reaction is getting less and less and less and less and less. Eventually there comes a point, Josh, where that nuclear reaction is not big enough to keep the mass out anymore, and it collapses. It collapses into what we call a white dwarf. What color do you think a white dwarf is? White. Do you think a white dwarf is hot or cold compared to a red giant? Hot. How big do you think a white dwarf is compared to a red giant or intermediate star? Because we know how to name stuff. Also, you'll notice, so again, Stage 3, the main sequence stage, really long. That's where our sun is right now. But then the collapse happens fairly quickly, relatively speaking. It happens over a few 100 million years as opposed to billions of years. Okay? Our sun is going to eventually form a red giant. We've run the numbers, and there's some leeway. It's possible when it expands into a red giant, it might swallow up the Earth, or it might end up just shy of the Earth. The Earth is either going to get boiled to a crisp because it's really, really close to the sun, or it might actually just get vaporized. The sun might actually completely swallow it up. It depends how we run the numbers. We're still not quite sure just how big the sun will get when it will form a red dwarf. But that's your preview of coming attractions. In about 4 billion years, Brooke, if you're still around. Okay. What that does mean, by the way, is if we want humanity to exist forever, we eventually got to leave the planet. We eventually got to leave the solar system. We eventually got to be able to do the Star Trek, go interstellar thing. Otherwise, we'll be gone. Okay? Then you get the white dwarf and a black dwarf. So some pictures for you. Here is a nebula. This is in Orion, the Hunter, which is a constellation you can see in the wintertime. The bright areas are hot regions where new stars are being formed. When I say being formed, again, Ibrahim, we're talking over hundreds of millions or billions of years. It takes a while on the cosmic scale. It's quick. Remember in the video we watched last day, we showed you the cosmic calendar, and you realized that humans have only been around for about 16 seconds on the cosmic calendar if we make the whole universe 1 year long. Anyways, on the cosmic scale, this is happening fairly quick. Relative to us, this takes a long time. But nebulae, the plural of nebula, they're very pretty. That's one of the first photos the Hubble Space Telescope took Still one of the most spectacular one. It's been nicknamed the Pillars of Creation. This is a star nursery. Stars are being born in this area. You may have seen it on posters or on t-shirts. So how does a star form? Let's get into more detail. So all stars form in nebulas. By the way, the plural of nebula is really nebulae, but I figured that would scare you, so I just put an S on the end of the word nebula, nebulas. Clouds of gas and dust, mostly hydrogen. When gravity causes some of the cloud to come together. And this forms a mass called a protostar. You may have heard the word prototype, which is like we haven't built it yet. This is our first attempt at seeing what it looks like. This is a protostar, a pre-star. You got everything in place, it just hasn't happened yet. Okay? By the way, you should know this, and maybe you don't. So gravity is the force that all masses have. If we are in outer space, and this was a rock floating in outer space, and this was also another rock floating in outer space, they are tugging on each other with a force of gravity. If you have patience, you will see that these two masses slowly, ever so slowly, that's why I said this doesn't happen over a fast time, slowly are attracted to each other. If you have a bigger mass, you have more gravity, so the Earth has a pretty big mass. The Earth has a pretty big force of gravity. Here, it's not slow, it's fairly quick, but you saw it attract the mass down. The bigger the mass, the more the force of attraction. But since we're talking about a cloud of dust, the masses generally are all initially pretty small. It's going to take a while for this to occur. So we have a protostar. We've got something kind of round-ish shaped, ready to go. Now what? As the protostar gets bigger, the temperature at the inside increases because you're pressing down, and all these atoms and molecules are moving together. Well, if you press your hands harder and rub them together, you get more heat. And so the temperature inside increases to about 10 million degrees Celsius. And hydrogen atoms fuse, forming He. What's He? See this good review, by the way? Helium. Okay. Helium is from the Greek word helios, which is the Greek word for the sun, because helium was first discovered by scientists by looking at the sun. There's a weird element there that we don't know what. Oh, helium. Then they also found it on Earth. But because helium is inert, it was tough to detect because it doesn't, right? It's one of the noble gases. It doesn't bind with anything, so it's really tough to detect it with our standard technology. And as soon as fusion starts to occur, Tensei, it now gives off heat and light. It's a star. That's like the let there be light, boom, moment. This reaction continues for millions of years, and you can, if you want to, I'll even write. Bigger stars last millions of years. Smaller stars can last billions of years. Let's talk about this nuclear reaction a bit more, Josh. So what's going on in a star? Hydrogen fuses, is pressed together to form helium, releasing energy. There's an equation that describes this. You may have seen the equation. It goes like this. E equals m. That's one of the things that Einstein came up with as an actual consequence of his theory of special relativity. He said, oh, by the way, it turns out energy can come from matter. Matter can turn into energy, and it's an awful lot of it. Eventually, the helium builds up, and it starts fusing. It starts fusing to form larger atoms. And the process continues. Okay? So if you look at this little picture that I added here, here's a hydrogen atom. It has 1 proton and 1 neutron. Here's another hydrogen atom. It has 1 proton and 2 neutrons. When they get pressed together, you can get a nucleus with 2 protons. That would mean it's element number 2, helium. And 2 neutrons, which is what helium wants. Oh, and you got an extra neutron kicking around, but that might get forced into something else. Okay. Some examples. If you combine 1 proton and 1 proton, hydrogen, 1 proton, plus hydrogen. By the way, I'm ignoring electrons because under that heat and under that pressure, electrons are ripped right off of the atoms. In fact, we say that it's something called plasma. Plasma is when you remove all of the electrons from the nuclei of the elements, and all you have are the nucleuses sitting there by themselves. The electrons are just spread out evenly everywhere. Okay? Well, Jolene, what's 1 plus 1? What's 1 proton plus 1 proton? What's element number 2 on the periodic table? So you can get helium. Oh, so now you have helium and hydrogen. Hannah, what's 2 plus 1? What's 2 protons plus 1 proton? 3 protons. That would give you element number 3 on the periodic table, which is? Yep. Now that you've got some lithium, Danielle, what's 3 plus 1 in your head, please? What's 3 protons and 1 proton? 4 protons. What is element number 4? Beryllium. Oh, and now that you have, like, you can even, instead of always just combining hydrogen, hey, what would lithium, 3, and beryllium, 4, give you? 7 protons, element number 7. This is how most of the most common elements are formed, up to iron. Every single element on that periodic table, up to the element iron, was formed inside the guts of a star during fusion. That's where they all comes from. All atoms up to the size of iron, can I use Fe because that's we can use our shorthand, are formed during the regular life cycle of a star, that long life cycle from the picture where I said the star was just doing its thing. Right now, our sun is fusing carbon and helium and fluorine and titanium and potassium, all the way up to iron. Now, the further up you go, the less of them there are because you need more and more energy to create it. Where'd the rest of the elements come from? The rest of the elements, everything after iron up to uranium, they're formed during a supernova. Massive, 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 massive explosions of large stars. Remember I said that large stars have a shorter life cycle, but one of the cool things is they often go supernova, and that's what's given all of the elements on the periodic table up to uranium. What about the ones after uranium? Those we've made in labs in particle accelerators. They don't exist in the universe on their own naturally. And just like that, there's the whole periodic table. Put your pencil down. Every one of you, Ibrahim, every one of you, Carter, every one of you, Brian, you're all children of the stars. You're all made of star stuff. Every atom inside of you came from out there somewhere. It required a star to explode and go supernova and give up its life, and eventually part of it became you, which is kind of cool. Or here's an old picture of me, technically. Or some quotes, says this: "Our story is the story of the universe, every piece of everyone and everything you love and everything you hate, of the thing that you hold most precious, was assembled by the forces of nature in the first few minutes of the life of the universe, transformed in the hearts of stars or created in their fiery deaths. And when you die, those pieces, your atoms, will be returned to the universe in an endless cycle of death and rebirth. What a wonderful thing it is to be part of that universe, and what a majestic story." Or, matter, atoms, matter flows throughout the universe from place to place, and Brooke momentarily comes together to be you. On the cosmic calendar, you guys exist for about 100,000th of a second. But the matter has come together to form you, Cole. Some people find that thought disturbing. I find the reality thrilling, says Richard Dawkins. And then after this, your atoms get passed back on. Right now, the odds are very good that all of you have at least one atom that Buddha had, that Christ had, that Muhammad had, that dinosaurs had, that, you know what, really anybody who lived more than about 150 or so years ago had, because those atoms have already been cycled all the way through. But even more than that, your star children. A little poetry today? A little poetry today. Put your pencils down, look up. So let's talk about what this video summarized, the life cycle of stars. Open your textbooks to page 371. You have this picture here. Let me talk about what it means. First of all, here is all stars come from nebulae, from a nebula, a cloud of dust. Matt, it depends how much dust there is. You can have a low mass star, look up, a low mass star, a medium mass star, or a big star. But these right here, these three here, are what we call the protostars. If you have a small protostar, it ends up forming what we call a red dwarf, and then collapsing into what we call a white dwarf, and its life cycle fairly long. Intermediate stars, like our sun, we say a main sequence star, and we say it has a mass of 1 solar mass. Our sun is defined as 1 solar mass. So if a star has 2 solar masses, it's twice as massive as our sun. Josh, you with me? Head up, okay? So in an intermediate star, a main sequence star, you get this long, hey, the star's just doing its thing. Then it can expand into a red giant and then collapse into a black dwarf. Or you can have the massive main sequence stars. These are about 100 solar masses, about 100 times bigger than our sun. And for these stars, they don't last as long, they burn faster. They can become a supergiant, they can explode into a supernova, and then collapse, and they can collapse into either a neutron star or a black hole. That's what this chart, Brady, is trying to get across. There's lots of information in that chart on page 371. It's in color, so I couldn't reproduce it for your notes. But did I tell you in your notes to turn to page 371? You know where it says low mass stars at the top of the page? Above it, why don't you write page 371 in your notes? So we're on the back page now, yeah? Is that right? Yeah. Right near the top of the back page, right above low mass stars, page 371. But let's go through this in some more detail. So here's a graph showing the lifetime of main sequence stars. If a star has a mass of 1 solar mass, it'll last about 16 billion years, we figure, give or take. 2 solar masses, it'll last about 2 billion years. And you can see big stars like 14 solar masses, they don't last very long at all on the cosmic scale. They last a few 100 million years, but that's still a long time relative to us. So low mass stars, if you want to, you can write next to that top row on page 371. They start small, they stay small, and they're called red Dwarfs. What color do you think a red dwarf is? Do you think it's a hot star or a cold star? Cold-ish. Do you think it's a big star or a small star? Because we know how to name stuff in astronomy. Okay? They burn very slowly. In fact, they burn so slowly, really, on this chart, we really should have had this way longer. Just couldn't fit it in. How slowly? Well, we think they may live 100 billion years. Our universe is about 13.4 billion years, so we figure these stars will last for a long time. Longer than the age of the universe thus far. Eventually, they become a white dwarf. Then they burn out. These are low-mass stars. Then we have intermediate mass stars. Hey, that's the middle row on page 371. Because they have more mass, they burn their hydrogen faster. They last only about 10 billion years, only. Okay? Close to the end of their life, they expand into a red giant. They shed most of their material. It sheds most of its material, and it collapses, becoming a white dwarf star and then a black dwarf star. The sun is an intermediate mass star. It's about 4.5 billion years old-ish. So it'll become a red giant in about 5 billion years, give or take. I think I said 4 billion years earlier. About 5. I think the best estimates right now, I think about 4.6, 4.8 billion years. I'm not going to be around, Kevin, so you don't care that much. So we have low mass stars. We have intermediate mass stars. What would we call the next one? What's the opposite of low? Hey, we know how to name stuff. High mass stars. Bottom row of page 371. These are some of the cooler stars in terms of interest. Intermediate mass stars are nicer because we think those are stars that might potentially have planets that support life, like ours. But the high mass stars are just cool. They're huge. They consume energy way faster. They live for only about 7 billion years, but actually there's a huge range. The really massive ones might only live for a few millions of years, up to billions of years, because there's some super, super big, massive ones out there too. They go really fast on the cosmic scale. They become supergiants. Hey, what do you think is bigger, a red giant or a supergiant? We know how to name stuff. And then they collapse in on themselves, causing dramatic explosions called, what were the explosions called? Supernova. One supernova, 2 supernovae, or novae. These can be so bright that they can be seen during the day from the Earth. There was one in around the year, I think 1066 or so. There are records. It was the Crab Nebula that went supernova, and you could see it during the daytime. So none has been that bright for about 400 or so years. However, you guys might get one. You might get something that's so bright that, like the moon, you can see it during the daytime too. We have a ticking time bomb nearby. Put your pencils down. You can find these if you download for your smartphone a good stargazing app, and there are good free ones out there. You can try and look at these with binoculars. But I told you we might get one during the day. It turns out we might. So Betelgeuse, however you want to say it, is predicted to go supernova soon. Matt, soon means on the cosmic scale sometime in the next 50 million years or so. But that is, on the cosmic scale, a ticking time bomb. Could go next week. We would probably be able to see it during the day, if it goes. If that star was about 12 to 15 times the size of the sun, it will collapse into a neutron star. What's a neutron star? A neutron star is unbelievably dense. So let's talk about density. You might recall we said density was how closely packed the atoms are. Both of these have pretty close to the same volume. Yes? Which one is denser? This one. It's very heavy. This is nothing compared to a neutron star. Lead is like helium compared to a neutron star. A star that was once 1 million kilometers wide will now be 10 kilometers wide. Smaller than Pitt Meadows. And it's crammed in unbelievably. Put your pencils down. So neutron stars. The star has ejected its outer layer, and it's the dense core left behind. You gonna make it, Matt? I got a couple more. That's if the star was about 12 to 15 times the size of our sun, if it has 12 to 15 solar masses. If it's a little bigger, if the mass was 25 times that of the sun, if it has 25 solar masses, it can become a black hole. A black hole is so dense, its gravity is so strong that nothing, not even light, can escape. We can see where black holes are because we see when we're looking at an area of space that appears blank, light from behind that blank area is being distorted. So light from stars behind the black hole is distorting. So we know, oh, something's got to be there. We can't see it, but it's strong enough to bend the light. That's a black hole. Turns out there's one at the center of our galaxy. Put your pencils down, look up.